We've discussed a lot of material over the course of this semester. Since the beginning, we've talked about operations, algebras, algebraic properties, groups, talked about what it means for two groups to be isomorphic. We've introduced the notion of an isomorphism in order to identify whenever two groups are isomorphic. We've talked about subgroups. We've talked about quotient groups. We've talked about bijective functions, normal subgroups. Most recently, we've talked about homomorphisms. Today, we're going to put all of those topics together in order to discuss one of the most important topics in all of abstract algebra, so important that it's called the fundamental theorem of group homomorphisms. We already talked about this a little bit in our most recent video. Whenever we looked at a homomorphism from a group G1 to G2 and noticed that the set of elements that got sent to the identity turned out to be a normal subgroup of G1, that's going to serve as the foundation for what it is we're going to talk about today. So, whereas last time we began the proof of the fundamental theorem, today we're going to build on that and complete it. Let's go to the whiteboard. So to set the stage for the fundamental theorem of group homomorphisms, we're going to start with two groups, G1 and G2, we'll call them, and we're going to assume that we have a homomorphism that takes G1 to G2. And for convenience, we're going to assume that the homomorphism is surjective. If it weren't, what we would focus on is the range of the homomorphism anyway. So just to make things a little bit cleaner, we will assume from the outset that our homomorphism is a surjective one. So what I have identified here, I have several points in G, and I've identified their images over here in G2. We never mentioned before that the identity element of a homomorphism has to be mapped to the identity element of the range, but it's a pretty straightforward proof. In fact, it's identical to the similar theorem for isomorphisms, and I'm going to ask you to do that as a homework exercise. So not only is E1 going to go to E2, but because this is a homomorphism rather than an isomorphism and bijectivity is not required, it's possible that there are other elements that are going to get mapped to E2 as well. And the focus of our last video was to prove that this set, we'll call it K, and I believe we called it the vanishing set of H. It's the set that takes everything to the identity element. We proved that the vanishing set always turns out to be a normal subgroup of G1. Well, because it's a normal subgroup of G1, we can talk about the quotient group of G1 mod K. Let's go ahead and illustrate the quotient group G1 mod K. So right, so that's gonna be all of the cosets of, so here's our K, has E1 in it, has several other elements that get mapped to E2. And then XK, for example, well, let's see, it's going to have cardinality of XK is going to be the same as the cardinality of K. So I've tried to illustrate that here in my picture. I have 4 elements in K, 4 elements in XK, coset YK, coset ZK. What the fundamental theorem of group homomorphisms is going to tell us is that not only is K normal, and therefore we get a quotient group, G1 mod K, but that this quotient group is going to turn out to be isomorphic to our group G2, to the range group of our homomorphism, right? So we're going to spend the rest of this video proving that there is an isomorphism from this quotient group to G2. Which function would you pick? What seems to be a natural one to try? Right? Where would you send, for instance, where would you send K? In other words, where would you send this coset that contains E1? Where would you send that to G2? Where would you send the coset that contains X? What seems to be a reasonable place to send that to G2? Just think about that for a moment. How would you define a function f from G1 mod K to G2 that you think just might turn out to be an isomorphism? Well, what we're going to do is we're going to define that function. We're going to define a function from our quotient group into G2 by sending, well, how about, doesn't it seem a natural thing to send the coset that contains X to what the image of X was under our homomorphism? Right, let's go back and look at the picture. Doesn't it seem natural to send K, right, the coset that contains E1, doesn't it seem natural to send that to E2? Doesn't it seem natural to send the coset that contains X to H of X? The coset that contains Y to H of Y, and so on. Doesn't that seem like the most natural function to work with, right? So we're going to go ahead and make that definition. We're going to define f to be the function that sends a coset xk, right, in our quotient group to the image of X under our homomorphism. This function is going to turn out to be an isomorphism, and that's the focus of this video. But there's a potential problem with this definition, and I'd like to illustrate what that potential problem is. Keep in mind, a coset has multiple elements in it. So whenever I say it seems perfectly innocuous to make this definition. It seems like, yeah, there's only one thing that xk is going to under this definition. But what if I picked another element, y, out of there, right? Of course, the cosets are the same. Xk and Yk are the same coset. But what would have happened if H sent X and Y to different elements? That'd be a problem, because now I have this function that's sending a coset to two different elements. That wouldn't be a function. That would not be well defined. So we need to show that that can't happen. So here's why. Well, let's see. So let's say we had that element in the coset xk, and well, what does that mean? That means that y is equal to x times something in k, and well, so where's h going to take it? Well, so h of y is going to be h of this x times k. But remember, h is a homomorphism. So I could write this as h of x, h of k. But remember what k is, right? K is the vanishing set. K is the vanishing set of our homomorphism, right? K was exactly the set that h took to the identity element E2. And so h of k is E2, and what I wind up with is h of x, right? So it turns out that this potential problem doesn't happen, right? H of x and h of y turn out to be the same thing, and so f really truly does take each coset to exactly one element. That's great, right? So that tells us, well, that tells us f is a function, right? It's a well-defined function. That gets us started, right? If I have a coset, can be represented in various ways, right? xk, maybe x prime k. But in that case, h of x and h of x prime are both the same thing, and so it doesn't matter which element I used to represent the coset. F of that coset is always going to be just a single value, right? Which is exactly what we needed. Let's check to see if f is a surjective function. Remember, we're going to show that f is a bijection. Now that we know it's a function, it makes sense to ask, is it one-to-one? Is it onto? Does it preserve the operation? Those are the three elements that we're going to need. Actually, yes, those are the three elements that we're going to need in order to prove that f is an isomorphism, right? It has to be a bijective function that preserves the operation. So let's work on the bijectivity, and in particular, let's work on whether or not f is surjective first. So how do we do that? Well, all right, so f is taking this quotient group to G2. So to be surjective, we would need to know that no matter what element we looked at in G2, there's some coset that gets mapped to it. How are we going to do that? Well, let's start with something in G2. And remember, we assumed that H was surjective. We presumed that H was a surjective function. And so since H is surjective, and H, remember, H is going from G1 to G2. So since H is surjective, there's going to be something in G1 that H maps to B. Right? There has to be something in G1 for which h of x is equal to b. Well, whatever that x is belongs to some coset. In particular, it belongs to the coset xk. And by definition of our function, xk is going to go to h of x. Right? So f of xk is h of x, but h of x is b. And so we found a coset. We found a coset in our quotient group over here that f maps to the element that we picked out of G2. And that does it. That tells us that f is surjective. Excellent. So what do we have? So reminding us how we've defined the function again. And we've shown so far that f is well defined, right? So it is a function. We've just shown that f is surjective. What should we do next? Well, let's finish the bijectivity part of the proof by showing that f is 1 to 1. What does that mean? Well, that means that any two distinct cosets are going to go to distinct elements of G2. Or conversely, if I have one thing in G2, that there can't be two things which map to it. So the standard way of looking at that is, well, let's let x, k, and yk be elements of G1 mod k, for which f of xk is equal to f of yk. Right, so we're taking, basically we're taking, this is a way of saying let's take something in G2, right? So this is one element of G2, and we're going to show that we can't have two different elements mapping to it by showing that xk and yk actually have to be the same coset. Okay, well, by definition of our function, f of xk means h of x, and f of yk means h of y. And the temptation here is to say, oh, well, h of x is equal to h of y, therefore x equals y. Well, that's a mistake, right? Because h is only a homomorphism. It's not necessarily one-to-one, right? So there's no reason on the surface to believe that x and y have to be equal. It's a common mistake to make that next step by saying that. So we're going to have to be a little cleverer. Let me multiply both sides of this equation by the inverse of h of y. Now, of course, what that gives me on the right-hand side is just the identity element in G2. And let's see what I have on the right-hand side. This is h of x. Right, another thing we have not specifically shown, although we did use it in our last video, was that a homomorphism has to send the inverse of an element to the inverse of the image of that element. Right, so this is actually the same as h of y inverse. I'm going to ask you to show that as a homework exercise. We did it. We did the similar result for isomorphism some time ago. It's basically the same proof, but just to fill in that blank, I'm going to ask you to prove that as a homework exercise. All right. So at this point, we have h of x times h of y inverse is the identity element in G2. And because h is a homomorphism, again, doesn't matter whether you look at the images first and multiply in G2, or you multiply in G1 and then look at the image, you get the same element. And so that tells me that x y inverse is equal to the identity element in G2. Oh, okay, that tells me that h times y inverse, that's in the vanishing set, right? That's exactly what this means, right? It means that this element is in the vanishing set. This element, that element is it's in K. It's in that vanishing set. And so xy inverse is equal to something in K. But that tells me that, let's see, so that would mean that I'm going to multiply both sides of the equation by y. Whenever I do that, that tells me x is equal to k times y, which of course is inside of, well, this is the right coset, ky, right? But k is a normal set, k is a normal subgroup, and so that's the same as yk. So that tells me that x is in yk. Well, cosets, as you'll recall, are either identical or disjoint. And since x is in yk, the coset that contains x must be the same as the coset that contains y. And that's what we needed to show. So if we start with a couple of cosets for which the image under F is identical, the cosets that we started with must have been identical as well. That shows that F is 1-to-1. Isn't that a clever proof? All right, so where are we in our proof now? We've got F is a function. We've got F is surjective. We've got F is 1-to-1. There's only one thing left, isn't there? We need to show that F is operation preserving. Here we go. Let's take a couple of cosets out of our quotient group. Let's start by multiplying them together in our quotient group. This is indicating coset multiplication. And then we'll look at the image of what we get. Well, by definition of coset multiplication, this is going to be x, y, k, right? That's going to be the coset that contains x times y. And so let's see, by definition of our function, right? Our function is sending the coset that contains x to h of x. And so this is the coset that contains x times y. So it's going to get sent to h of x times y. So that's just by definition of F. H is a homomorphism. So H itself preserves the operation. So I can write that as h of x times h of y. But h of x is f of xk. H of y is f of yk. So there it is. We have that if we multiply first in our quotient group and then apply F, we get the same thing as if we had applied F individually and then multiplied in G2. So F is operation preserving, and therefore we have finished the proof that F is an isomorphism. We did it. We did it. So let's draw a picture just to bring this all together. Right, so what did we do? We started with two groups, G1 and G2. We identified a homomorphism between them. We assumed it was surjective, right? And we looked at the set of all elements that H took to the identity, right? So all of these go to the identity element. And we proved that K is a normal subgroup of G1. Well, that tells me that the cosets, so let's see, if I wanted to look at XH, that's going to have X in it as well as probably some other things. Well, definitely some other things if K had multiple elements in it as well. Right, we can, for Y down here, we're going to have a coset that contains Y. Right? And if we define the function that sends k to the identity element that sends xh to hx, that sends yk to hy, and so on, that this function f that sends the coset that contains an element to the image of that element under x is an isomorphism. It's one-to-one, it's onto, and it preserves the operation. So here's a statement of it right here. If H from G1 to G2 is an that's not right. Homomorphism is a homomorphism, then the vanishing set K of H is normal, and the group of cosets of K is isomorphic to G2. Therefore, what we have is that every homomorphic image of a group G is, you almost want to say is a quotient group of G. Technically, it's isomorphic to a quotient group of G, but we would not distinguish between the two, right? From an algebraic viewpoint, they have exactly the same structure. We think of them as the same. And so this is the fundamental theorem of group homomorphisms right here. Now, it's kind of a natural question at this point. We've just shown that every homomorphic image of a group G is isomorphic to a quotient group of G. Is the converse of that statement true as well? In other words, if I've got a quotient group of a group G, does it also turn out to be a homomorphic image of G? Well, it turns out that the answer to that is yes. And here's the idea. So if we're going to talk about this, we have to start with a normal subgroup of G, right, in order to talk about a quotient group at all. So let's let H be a normal subgroup of a group G. And so, right, so we've got G, we've got a bunch of elements in G. Here's our normal subgroup. Our normal subgroup is going to contain the identity element. And I can partition the rest of G up into cosets of H. And since H was normal, this collection of cosets forms a group, right? So this, if I'm focusing on the cosets as my elements now, that would be my quotient group of G. And how about, let's see, what's a natural function to claim might be a homomorphism? Where should I send, for instance, where should I send E? To what coset should I send E? Again, what I'm asking, right? I'm trying to decide that G mod H is a homomorphic image of G, right? So I need to define a homomorphism from G to G mod H. I need to define a function from G to G mod H and prove that it turns out to be a homomorphism. And I think the most natural one in the world is the one that sends E to the coset H, that sends X, in fact, everything in X, to the coset that contains it, and so on. Right? So it seems like a natural candidate for a homomorphism from G to G mod H would be the one that sends each X to its coset. This turns out to work, and I'm going to ask you to show that it works as a homework exercise. So here's your homework. Let's start with a homomorphism from G1 to G2. Let it be a group homomorphism. And let's let E1 and E2 denote the identity elements of G1 and G2. So E1 is the identity of G1, E2 is the identity of G2, right? And let's see, so the first couple of homework exercises are gonna ask you to clean up a couple of things in the proof that we glossed over, right? Prove that H has to take E1 to E2, and also prove that H has to take the inverse element of an element X in G to the inverse of the image of X under H, right? Also like you to do exercise 200. Look that one up in the course notes. And then finally, what we just talked about, want you to prove that every quotient group of a group G is a homomorphic image of G, right? No, so use the function that we just defined a moment ago, the function that took G to a quotient group G mod H by sending X to the coset that contains X, and prove that that turns out to be a surjective homomorphism. That's what homomorphic image means, right? It's that there's a homomorphism between it, and the image part means that that is a surjective function. So with this video, we've hit a milestone in the course. We've proven one of the most important theorems in all of abstract algebra, the fundamental theorem of group homomorphisms. You should make sure that you can prove that theorem on your own. I want you to be able to go through the details of that theorem. That makes a fabulous final exam question, or at least portions of it would be a fabulous final exam question or set of questions. So please make sure that you can carry out the details of that proof on your own. Until our next video, I hope that you will stay well, stay safe, and I'll see you then.